Okay, so thank you everybody for attending this online seminar of the IFT series. Today we have with us Petraki from Sorbonne, LPHTE, and Nikhef, and she will speak about dark matter. Thank you very much.
Okay, thank you very much. Thank you for the invitation. All right, so I'm going to talk about dark matter bound states, in particular about the relevance to the dark matter production in the early universe. So, because essentially all of the talk will be about dark matter production in the early universe, I thought I would start with sort of a trivial statement about why do we care about how dark matter was.
Sorry, I had a lot of echo. Does everybody is the same? I'm sorry for apology.
Yes, yes, but we have tried for a long time before, and this is the best we achieved.
Wow. Okay. Apologies.
Sorry.
Okay. Go ahead, please.
Maybe I'll turn it down a little bit my microphone and let me know. I'll speak loudly, and so let me know if it's a bit better. So
now it seems a bit better. Yes, thanks.
Okay, good. All right. So why do we care about the production of dark matter in the early universe? We care about because it depends on the coupling of dark matter to other particles, and this is of course how we expect to detect dark matter and understand the properties of dark matter. So the most famous dark matter production mechanism is the so-called thermal freeze-out. And let me briefly review this mechanism. The idea is that dark matter was in chemical and kinetic equilibrium with the standard model, with the primordial plasma in the early universe when the temperature was high, via very, very rapid annihilation and pair creation processes. Thermal equilibrium means that the density of dark matter was determined by the temperature of the universe. And initially, dark matter was relativistic when the temperature was high enough. Eventually, the universe expanded, it cooled down, dark matter became non-relativistic. This means that the density of dark matter became exponentially suppressed. Eventually, the dark matter particles stopped finding each other, the self-destruction stopped, and this means that the dark matter density froze out. So we can easily calculate what is the relic density of dark matter produced via this mechanism, and famously we find that we get the observed dark matter abundance if the annihilation cross-section times relative velocity is about 1 picobarn. And now, of course, because the 1 picobarn is of the order of the wake interactions of the standard model, this was deemed to be the WIMP miracle. While this mechanism originally was motivated by WIMPs, meaning particles coupled to the weak interactions of the standard model, so the W and the Z bosons, and probably the Higgs, it was quickly generalized to include other particle physics scenarios. For example, dark matter coupled to the standard model particles via new interactions, for example, new gauge interactions or interactions of other kind, that quite often are described via effective operators, like the one I have written down here. And then there was yet another generalization of this scenario in sectors that are actually hidden, which means that dark matter doesn't couple necessarily directly to the standard model particles, but instead it couples to some dark sector light particles, and then the dark sector force mediators couple themselves to the standard model via a small coupling. So at least in the first two cases, the fact that dark matter is hypothesized to have been produced thermally in the early universe means that the coupling of dark matter to the standard model is not totally negligible, and this means that it can give rise to detection signatures. So this picture here summarizes the three main detection signatures that have been the basis of the experimental program for dark matter in the past decades. And these signatures are the production of colliders via the production of dark matter at colliders via collisions of standard model particles, the indirect irradiative signals expected from the dark matter annihilations inside galaxies that can produce standard model particles, and also the scattering of dark matter, the last scattering of dark matter in underground targets. Now, spoiler alert, we haven't found anything so far. So the question is, what do we do now? And of course, we would like to diversify our dark matter searches and extend them to reach other regions and other models. There are broadly two directions. We can either consider heavier dark matter or we can consider lighter dark matter. The lighter dark matter part is something that has been developing a lot in recent years, and it is very promising because there is a whole host of new directed action experiments that have been proposed, and some are being built or are built. And so it is very interesting to explore sub-TeV dark matter. But heavy dark matter remains quite promising and interesting, and in fact, we're currently also at the dawn of the exploration of the multi-TeV regime. We do have many existing and upcoming indirect action experiments, such as Higgs, CTA, IceCube, that will be probing the multi-TeV regime. And in addition to that, in fact, it remains theoretically motivated in the very standard WIMP dark matter scenario. Simple implementations of this scenario actually do live in the multi-TeV scale. And so we can ask, and if we actually care also about thermal-relic scenario, not necessarily WIMPs, in fact, thermal-relic dark matter can be as heavy as a few hundred TeV. And so this is a question we can ask more precisely. How heavy can thermal-relic dark matter be? And not only that, but if we really want to explore the heavy dark matter possibility, heavy thermal-relic dark matter, then we should also ask what are the underlying dynamics in such kind of models in the multi-TeV regime. So what happens is that if dark matter is very heavy, things change a little bit from with respect to what we kind of were used to in the sub-TeV regime. If dark matter is very heavy, then and it couples. If dark matter is very heavy, then it is likely that the force mediators to which it couples are lighter than the dark matter itself. In fact, it can be that there is a hierarchy between the mediator mass and two other very important scales, the so-called Bohr momentum, which is the mass of dark matter or the reduced mass of two interacting dark matter particles, times the coupling by which they interact, or the de Broglie wavelength of, or the inverse, the Broglie wavelength of the two interacting particles. And the reason that this is happening is that, well, if we of course, the mediators can be even heavier, but if the mediators are very heavy, then the interactions they mediate will be very insignificant, and we will not have a successful dark matter, thermal-relic dark matter scenario. So this hierarchy appears because if we insist that the interactions of dark matter are fairly significant. And this is not something that becomes important within a very restricted class of scenarios. This is important every time. Everything that I will say will be important every time the mediators are much lighter than dark matter. This includes the self-interacting dark matter scenario. This includes scenarios that occasionally come up that aim to explain astrophysical anomalies. This includes WIMP dark matter with multi-TeV scale masses. Of course, again, the weak interactions of the standard model have been the paradigm of contact interactions in particle physics. Nevertheless, if the interacting particles are heavier than a few TeV, the weak force mediators are light with respect to the interacting particles, and the weak interactions manifest as long range. And in fact, the long range dynamics that I will describe concern also WIMP dark matter in the sub-TeV regime in scenarios where dark matter correlates with colored particles, as I will talk about in more detail. Okay, so So what changes if the interactions manifest as the long range? Well, there are two things that happen. One is more well known perhaps than the other. The first thing that was observed and calculated by people was the so-called Sommerfeld effect. So when the particles interact by a long-range force, the wave function gets distorted. So the wave function is not a plane wave anymore. And this affects all of the cross-sections of the processes to which the two interacting particles participate. Now, this is the first thing that we may notice. However, there is a much bigger host of effects that are actually due to the fact that long-range interactions imply the existence of bound states. And so this is what I will mostly focus on. Now, and so what, more precisely? What is the matter that we have the Sommerfeld effect and bound states? Well, the Sommerfeld effect, as I said, affects all of the interaction cross-sections, and therefore it affects dark matter annihilation in the early universe, it affects dark matter freeze-out, and this means it changes the correlation of parameters that give the observed density, and of course this implies, this changes the experimental signatures. And also the same effect is important for indirect detection signals. It changes the rates the predicted rates. It gives rise to a velocity dependence on the annihilation cross-section, and also it gives rise to resonant effects. What do bound states do? Well, they do all of the above, and they do a few more things. So we can have unstable bound states, so particle and particle bound states, positronium-like bound states, which form and then decay. And this means that there is essentially an extra annihilation channel for dark matter. This extra annihilation channel affects the dark matter freeze-out, and also indirect detection, and because it can give rise to novel indirect detection signals, because in fact the formation of bound states is also always associated with dissipation of energy. The energy that is dissipated, usually radiatively, can be detectable, and this is a novel kind of indirect detection signals, besides the radiation that is emitted when the unstable bound states decay. So these are two different things. We'll only talk about the effect of bound states on freeze-out. In addition to unstable bound states, there can be also stable bound states, and the formation of stable bound states, of course, can affect the dark matter phenomenology, in fact, even more dramatically. And this is something that's particularly important for asymmetric dark matter models. Okay, so I have the ambition to talk about many things, but we'll see how far we get. So we'll start with a dark U1 sector and showcase the effect of bound states on the dark matter freeze-out. This will give me enough tools to talk about the relation between the unitarity limit and long-range interactions. And then I will discuss other scenarios, neutralino score annihilation scenarios in supersymmetry, and also the role of the Higgs as a light force mediator. Okay, so let's start with a simple dark U1 model. We will assume that dark matter is a pair of Dirac fermions coupled to a dark photon that we will assume is very light or massless. Then in this simple scenario, dark matter can annihilate into two dark photons. The annihilation cross-section times the relative velocity is, first of all, the so-called the tree-level part, which is this constant factor, alpha square over m square. But because the two particles interact via a light mediator, their wave function is distorted, and this is represented diagrammatically via this ladder diagram, the exchange of infinite dark photons. And the effect of these diagrams, which we calculate simply by, of course, solving the Schrödinger equation with a Coulomb potential, the effect is that they change the annihilation cross-section by a factor that depends on alpha over v. And this factor is plotted over here. It is this blue line. This is the so-called Sommerfeld factor. So we can see that at large velocities, nothing is happening. At low velocities, because the wave function of the incoming particle is distorted, and because the interaction is attractive, the annihilation cross-section increases. And so low velocities are, of course, when we thermally average the dark matter over the dark matter population in the real universe, the low velocities correspond to low temperatures. Okay, but besides the direct annihilation dark photons, we also have another important process which had been neglected earlier on, and this is the formation of positronium-like bound states, particle and diparticle bound states with emission of a dark photon. And so you can see the diagrams over here. Now, we can easily find the cross-section for these processes by opening an old quantum mechanics book, and we will see that the cross-section times relative velocity factorizes in a similar way to the annihilation one. So it is this constant part times a factor that depends on alpha over V. And you can see this factor plotted here on the right. And what you may observe here is that in the entire velocity range where the Sommerfeld effect is important, so when the velocity is roughly smaller than alpha or of the same order, bound state formation is actually the dominant inelastic process. In this particular model, it is larger by a factor of 3 with respect to the direct annihilation. Why is this important? This is important because these bound states are unstable and they can decay. Depending on their spin, they can decay into 2 or 3 photons. So this is para and orthopositronium. And if they decay, of course, they deplete the dark matter density. So we should really redo the freeze-out calculation and redetermine the predicted coupling as a function of the dark matter mass that gives the desired dark matter density. And you can see here the difference between considering 3-level annihilation, so perturbative annihilation, Sommerfeld enhanced annihilation, and annihilation plus bound state formation. Just to remember why this is important because this relation of parameters determines the experimental signatures of dark matter today, so direct and indirect detection. And what I would like to point out here, we should keep in mind, is that we see that these effects, the long-range effects, appear at roughly few TeV, the few TeV mass range. And there is another comment here on the so-called unitarity limit that I will discuss in a few slides. Okay, so now that we have seen one example of all this, the simplest one, we can try to, first of all, make sense of what just happened. And so this is a very beautiful piece of physics that I was very happy to learn. We don't usually learn it in our field theory classes, although people who are familiar with non-relativistic effective field theories, of course, know this very well. So let me go through this. So the question is, how come we got all these effects, the Sommerfeld effect and bound states, by just adding diagrams that are seemingly suppressed by higher orders in the couplings of the theory? So the ladder diagrams I just showed is actually they represent a sum of diagrams that contain an increasing number of gauge boson exchanges here, or whatever boson we have in our theory. So why does this sum give us something that's important, an enhancement and bound states, instead of giving us just unimportant higher order corrections? What is happening over here? And so what is happening is that, of course, in calculating these diagrams, we have to integrate over the loop momentum. And among the whole integration, within the whole integration region, the momenta that contribute the most are the momenta that scale with the coupling itself. So the region of momenta that contributes to these diagrams the most is when the momentum transfer is of the order of the reduced mass times alpha. So alpha here is g squared over 4 pi. And the energy transfer is the momentum, the free momentum squared over the reduced mass, so it scales as alpha squared. In this pixel, the interacting particles are merely on shell. They are off shell only by a small amount of energy, and this energy again scales with alpha squared. So to convince ourselves about it, we can actually calculate it right here. So we can take first the one boson exchange diagram. At the level of the amplitude, we will get a factor of alpha because of the 2 vertices. And then we have the one boson exchange. The momentum transfer, the free momentum transfer dominates over the energy transfer because they differ by a factor of alpha. So the propagator of the dark photon here gives me 1 over mu alpha of the squared. So this diagram scales as 1 over alpha. Now let us examine the one loop. I get an extra factor of alpha because of the extra 2 vertices. Then I have to integrate over the loop momentum. The energy factor gives me alpha squared. The free momentum gives me alpha to the cubed. Then the fermion propagators, again, the fermions are off cell by a small amount of energy, which scales as alpha squared. And then the extra photon propagator goes as mu alpha squared. And if you count the powers here, you will see that the powers of alpha cancel. So what do we understand from here? 2 things. One, that all of these diagrams add up coherently. They are all of the same order. So when I add them up, I get something large. And overall, they scale as 1 over alpha, which is why these non-perturbative effects show up. This is why we call them non-perturbative, not because the coupling is large, but rather because they scale as 1 over a small parameter. So this is the origin of these effects. Of course, all of this counting would fail if the boson propagators contained a mass. And from here you can see that it would fail if the gauge boson or the mediator mass were larger than simply the Bohr momentum. Right? So, and this is indeed the condition for the existence of bound states and for the Sommerfeld effect. So this counting is a bit more specific for the bound states. What happens with the scattering states? It's quite similar. For the scattering states, we have one extra diagram, which is the free diagram. The counting here is a bit more complicated because the energy and momentum exchange scale both with alpha and with the relative velocity. So the momentum, the relative momentum, so the reduced mass times the relative momentum is the expectation value of the momentum in the center of mass frame. If I turn off the long-range interaction, this is the momentum. If I turn it on, the scattering state is not a plane wave anymore, so there is a quantum uncertainty. This quantum uncertainty scales with alpha. And so the Sommerfeld effect appears when the quantum uncertainty, which scales with alpha, is of the order of the expectation value, the classical value. And this is exactly what we saw before in the U1 example we examined. When alpha becomes of the order of V, this is when the Sommerfeld effect appears. Again, because the quantum uncertainty becomes of the order of the expectation value. Okay, so I think this is all very interesting physics, and we will now use it to understand the connection between the unitarity limit and long-range interactions in the non-relativistic regime, and the implications for thermal-relic dark matter. So the unitarity of the S matrix, it has been well known since long time that the unitarity of the S matrix puts an upper limit on how large the inelastic cross-sections can be, and also the elastic. But here we will care about the inelastic. So this is the upper limit. This is the upper limit on the inelastic cross-section. The upper limit can only depend on the kinematic parameters. The kinematic parameters are the mass and the momentum. What is important to notice here is that the upper limit on the inelastic cross-section scales as 1 over the momentum squared, not as 1 over the energy squared. Now, in the high energy regime, the momentum is the energy, and this upper limit reproduces well-known results. But in the non-relativistic regime, the momentum is actually the reduced mass times the relative velocity. This will actually give us an insight on what is going on when we approach the unitarity limit. I just want to point out here that, the unitarity limit physically means that the probability for inelastic scattering is equal to 1. And so this is the physical meaning. And of course, we expect that it may be realized, it may be attained when the couplings are large enough, right? Okay, so keeping in mind the scaling of the unitarity limit with the velocity and the mass, let us see what, first of all, this means for dark matter. Back in the early 90s, Gristin and Kamiankovsky wrote a seminal paper where they pointed out that this upper limit on the inelastic cross-section implies an upper limit on the mass of thermal-relic dark matter. This is because indeed to have thermal-relic dark matter, we need a certain annihilation cross-section. This is the one we need over here, today's value of the canonical cross-section. This cross-section has to obey the upper limit on the inelastic cross-section. And from here, by plugging in a typical value of the relative velocity during freeze-out, we can find out an upper limit on the mass of thermal-relic dark matter, which is of the order of 100 TeV. Now, there were two assumptions made in this paper. One is that they explicitly write that one does not expect the 1 over v scaling of, one does not expect that the annihilation cross-section times relative velocity scales as 1 over v for annihilation channels in a non-relativistic expansion. And the other one is that the S wave yields the dominant contribution to the annihilation of dark matter. So what I would like to do is I would like to question these two assumptions and show that actually they are not true, quite the opposite. And the reason I would like to do that is because this will allow us to determine the unitarity limit of the mass of thermal-relic dark matter more precisely. But even more importantly, it will allow us to understand what can be the underlying dynamics of viable thermal-relic dark matter models in this regime. So let us start first with the velocity dependence of the unitarity limit. And ask the question, what kind of interactions can actually realize this unitarity limit? Because if we do care about 100 TeV dark matter, we must know what kind of interaction can produce a cross-section as large as the unitarity limit. So this is the question we need to answer. We know that contact type interactions, so interactions mediated by a heavy mediator, give rise to annihilation cross-sections time relative velocity that are either constant or they scale as higher powers of the velocity. So if I make this assumption that I have a contact type interaction that realizes the unitarity limit and go calculate the upper limit of the dark matter mass, then I have automatically made a mistake, because in the early universe, of course, I have to thermally average, first of all, of the thermal population of dark matter particles. So so what I have to do here is I have to choose a particular value for the velocity. Otherwise, I cannot compute the unitarity limit. And the question is, what is this value? If I choose a certain value, then particles that have a larger velocity, their unitarity limit is lower. And I have automatically violated the unitarity limit for those particles. And particles that have a smaller velocity, their unitarity limit is larger, and so they have not saturated their unitarity limit. So the calculation is not correct if we do it this way. But even if we don't care about the early universe and dark matter, the scaling of the unitarity limit of the cross-section, if we compare it with a constant sigma v, implies that a particle that has saturated the unitarity limit at a certain velocity, then with an infinitesimal change in the velocity, it either violates unitarity or does not saturate it. And this doesn't quite make any sense. So something has gone wrong, and the question is what has gone wrong. And so we can find the answer in considering long-range interactions. So let us take the example we had before, the annihilation cross-section of two Fermions into two dark photons, light dark photons. We have this constant factor for sigma v that comes from the tree-level cross-section, enhanced by the Sommerfeld factor that you see over here. We can take the limit of large couplings, because this is where we expect the unitarity to be saturated at large couplings. This limit here is the same as taking the limit of small velocities, large couplings or small velocities is the same here. And what you see is that we get sigma v that is proportional to 1 over v. So we actually recover the velocity dependence of the unitarity limit. So we definitely know that what Grist and Kamienowski wrote down, that the scaling is not physical, that is certainly not correct. We do have a very specific example where it appears it's certainly physical. And because it is physical, we can interrogate it a bit more and understand what's going on. So let us go again back to conduct type interactions. If we assume that we have a conduct type interaction that kind of saturates or approaches the unitarity limit, then well, we have to bound our conduct type interaction, which scales typically as a coupling squared times the energy squared, here is the dark matter mass, over the mediator mass to the fourth power. This has to obey unitarity. From this inequality, we find, first of all, that the coupling has to be large. This is no surprise. Of course, the coupling would have to be large to attain the unitarity limit. But besides that, if we reshuffle the parameters here, we find that the calculation that has led to this cross-section, the perturbative, the cross-section that we've been using, this calculation violates unitarity when the mediator becomes lighter than a certain scale. And what is this scale? Well, this is actually the Bohr momentum. Now, every time we have a comparison between scales, and this comparison tells us that our calculation failed, and this is what tells us here because we violate unitarity. Every time we have a comparison between two physical scales, we know that there must be a new effect at play. And this new effect is indeed the long-range interactions. This condition is exactly the condition for an interaction to manifest as a long range. So if we now include the Sommerfeld effect, as we saw before, the scaling of the cross-section is very different. And when we bound the cross-section with the unitarity limit, what we find is that, of course, at large enough couplings, unitarity is again violated, meaning that our calculation fails. This happens at a constant value for a dimensionless parameter. Of course, we need to do something at this point to cure our calculation, again, to correct our calculation. But this is very different from the situation we had before. Having an upper limit on a dimensionless parameter is not a comparison between two physical scales. It is how perturbation theory is supposed to work. When the coupling of the dimensionless parameter becomes large enough, of course, we have to include higher order corrections in our calculation. This is how it's supposed to work. This comparison, this upper limit of the coupling, does not signify a new effect, but the comparison we have here on the left signifies a new effect. So this means that we should definitely take into account the long-range behavior, the velocity dependence of the unitarity limit on the cross-section seriously. We know where it comes from. It comes from the long-range behavior of the underlying interactions. And if we care about the upper limit on the mass of thermal-relic dark matter, then what we should do is we should thermally average properly the cross-section. And then what we will find is that the unitarity limit on the dark matter mass is a bit higher than we had previously estimated. The values you see here are still hypothesized as wave annihilation, and this is the second thing that we should question. So Grist and Kamienowski had claimed that the S-wave annihilation is indeed the most important contribution to the annihilation of dark matter, and this is because indeed when we have conduct type interactions, we can expand them in the relative velocity, and the S-wave contribution gives the dominant contribution. The higher partial waves are suppressed by higher powers in the velocity. However, the situation is very different for long-range interactions. So we saw before an example of an S-wave process where when we include the Sommerfeld effect, what we get is a scaling of sigma v as 1 over v, the same as the unitarity limit. Now let us examine a process that is p-wave. A p-wave process, the perturbative part scales indeed as v squared. The Sommerfeld factor is actually different than it is for the S-wave. It includes the S-wave factor and includes this extra part here, which at the limit of alpha over v becomes alpha over v squared, and this v squared cancels this v squared. And what you see here is that we actually recover the 1 over v scaling of the unitarity limit. In fact, we should have known that because unitarity tells us so. The unitarity limit of the cross-section scales the same with the velocity for all partial waves, not just the S wave. So we should have expected that at large enough couplings, if we do our calculation correctly, we should recover the same scaling with the velocity. And so this kind of refutes the argument that higher partial waves are suppressed by higher powers in the velocity. They are not when we're close to the unitarity limit. But in fact, what you can see here is that the separation in v squared that exists in the perturbative regime and at high velocities, this separation actually has given its position to an alpha square separation. And this makes sense because before we saw that alpha is actually the quantum parameterizes the quantum uncertainty in the velocity. So what has happened here is that when alpha is larger than v, alpha takes the position of v. And so if this is all of the story, then perhaps in the end, Grist and Kamienkovsky were right to take into account only the S wave, because indeed higher partial waves are suppressed not by higher powers in v, but by higher powers in decoupling. The thing is that this is not the whole story, and the reason it's not the whole story is because we have bound states. And so in the example we saw before, we saw that we have the annihilation, the direct annihilation of dark matter into two dark photons, and this is dominantly an S-wave process. But we have also bound state formation, which here is a P-wave process for capture into the ground state at least, because we need to we need to account for the angular momentum for the spin of the photon, so we need to start from an L equal 1 state. And what we saw before is that the cross-sections for these two processes are actually the same up to a factor of 3, bound state formation being stronger than annihilation. They are of the same order. And the reason they are of the same order is, well, there are many reasons. There is only one coupling here for one emitted photon. But then a lot of the reason is also that, as we saw, the ladder of the bound state brings down powers of alpha, because the momentum exchange along the dark photons in this ladder diagram scales as alpha. So, so now that we have put all of the physics together, we understand that what's going on here, and we can conclude that for the purposes of dark matter, higher partial waves can be important. In fact, they can be even more important than lower partial waves, and then we should consider them when we estimate how heavy dark matter can be. But for me, the most important conclusion here is not necessarily what's the upper limit of the mass of thermal-relic dark matter, which apparently doesn't exist, because how many partial waves we should consider depends on the model. How many of them are important depends on the model in the end. But the most important conclusion here is that we see that in variable thermal-relic dark matter scenarios, there is, to reach the unitarity limit, which is at around 100 TeV, the interactions must manifest as long range. This is what the upper limit of the cross-section tells us. And if this behavior appears at the 100 TeV regime, then it will also appear a bit below that. It will appear at 10 TeV or a few TeV, because of course the cross-sections vary in a continuous manner with the parameters. And so this means that in variable thermal-relic dark matter scenarios, we should expect long-range behavior at the multi-TeV regime. Exactly where the long-range behavior appears depends on the model, but this is where we should expect it. And this, of course, is important for dark matter production in the universe and all the experimental signatures of dark matter. So let me now discuss more complicated scenarios. Let us return to the famous WIMPs. What happens with WIMPs? Well, the long-range effects will appear when the SB2 coupling times the dark matter mass is of the order or exceeds the mass of the weak mediators, and this we can easily estimate that this happens at around 3 TeV. Now, calculations have been done in this respect. The simplest models one can consider are models where dark matter is a pure multiplet, so a triplet or a quintuplet or higher multiplets. The triplet in particular is winner-like dark matter that appears in the MSSM. Because for winner-like dark matter, the freeze-out calculation predicts a mass of the order of 3 TeV, and this is of course very close to the threshold for the appearance of long-range effects. It turns out that for winner dark matter, only the Sommerfeld effect is important. Bound states are not important, at least for freeze-out. For the quintuplet, bound states are very important. They do increase the predicted dark matter mass significantly. But what I would like to discuss in more detail are scenarios where we have, instead of having a pure multiplet, we have the dark matter comes from mixed multiplets. So we have scenarios where dark matter is a linear combination of the neutral component of more than one electroweak multiplets. And in these scenarios, typically, especially if the masses of these multiplets are similar, co-annihilations become important in the early universe. So we'll discuss two different types of scenarios, neutralino quark co-annihilation scenarios that are motivated by supersymmetry and Higgs portal models. So one of the last refuges of the neutralino dark matter are scenarios where the neutralino, the lightest supersymmetric particle, is nearly mass degenerate with the lightest quark. The reason that this is viable is because the jets produced at colliders are soft, so they evade detection. But there is also another reason for which these scenarios are interesting. And that reason is that in order to produce the measured Higgs mass in the MSSM, what we need is to have a large coupling between the stop, a large supersymmetry breaking coupling between the stop and the Higgs. So I'm talking about the A terms. So what this coupling of the Higgs and the stop does is that it splits the two stop eigenstates. One becomes very heavy, the other one becomes very light. The light one comes close to the neutralino mass. And so this is how this scenario comes about. And again, it has two benefits. In some sense, it evades constraints and it produces the observed dark matter mass. Now, if this is so, if the neutralino is nearly mass degenerate with the lightest quark or the lightest stop eigenstate, then what happens is that the dark matter density in the early universe is determined by not only the self-annihilations of the neutralino, but also the co-annihilations of the neutralino with the stop, so the next to lightest supersymmetric particle, and the self-annihilations of the next to lightest supersymmetric particle. So what we should consider is the total density of the two species, and we should consider the total annihilation cross-section, where all of the contributions are weighted with the corresponding densities. But if we now put into the game the self-annihilations of a colored particle, of a quark, then QCD becomes important. And we should try to, if we want to accurately compute the dark matter density and map out the parameter space of these models and compare it with experimental constraints, we should really take into account all of the QCD effects here. So people have taken this quite seriously, and they have really calculated this kind of thing. So QCD corrections, radiative corrections, and of course the Sommerfeld effect that is due to the gluon exchange between the interacting quarks. Now, it turns out that one of these effects that are hard to calculate, the Sommerfeld effect is probably the most important, broadly speaking. But if this is so, there's an elephant in the room, and the elephant is that if the Sommerfeld effect is important, then bound state formation is important. So we should really take into account the formation of stoponium and the decay of stoponium. So to do that, we use the toy model, not the full MSSM, because that's complicated. So we use a model where, so we will assume that dark matter is the neutralino, and then it co-annihilates by some undetermined processes with the lightest stop, a colored a scalar triplet under SU3. And we will consider only the self-annihilations of the colored superparticle, or of the colored particle. So there is some group theory to be done here. So we have a triplet and anti-triplet interacting. This gives an SU3 singlet and an octet. These two states have different potentials. One has an attractive potential, the other one has a repulsive one. The attractive one allows for bound states. So what can happen here is that a quark and a quark pair can combine, can emit a gluon and form a color singlet bound state, which can then decay into gluons via the standard processes via which also these particles annihilate. So here are the cross-sections. In comparison of the cross-sections for bound state formation and annihilation, the blue lines are annihilation, and the red line is bound state formation, capture of the color octet state into a color singlet bound state. And what you can see here is that for a range of parameters, when alpha is around, or when the velocity is around of the order of the strong coupling, and the strong coupling here will be of order 0.1 because we care about multi-TeV scale masses. So around this range, the bound state formation process actually can exceed annihilation by more than one order of magnitude, and that is rather significant. So if we now do the freeze-out calculation again, then the two free parameters of this model is the mass difference between the dark matter and the correlating partner, the colored particle, and the dark matter mass. And what we can see here is the determination of these parameters in order to get the observed dark matter density. Now, what you see here is that when we include bound state formation, then of course the predicted splitting increases and the predicted dark matter mass increases. Why is this important? Well, it's important because colliders care about the mass splitting. Remember that these scenarios evade detection exactly because the mass splitting is predicted to be small. Now, if we take everything into account, we find that it's actually larger than what we thought it were, then this may mean that actually we can probe these scenarios. And of course, the dark matter mass is important for indirect detection experiments. And if we also care to tell how important this effect is with respect to the observed dark matter density, the width of the bands here is the 3 sigma uncertainty in the experimental uncertainty in the dark matter density. And the effect of on the dark matter density, you can see it on the right plot, and you can see it's of the order of a factor of a few. Okay, so let me quickly pass on the standard model Higgs. So I said before that in this class of scenarios, the stop, so the colored particle is actually, it usually has a large coupling to the Higgs. And so this may mean that actually the Higgs may act as a light force mediator. So let us examine this. We will extend our toy model by a coupling of the colored particle to the Higgs boson. And what happens here is that instead of having the non-relativistic potential, now instead of just having the gluon exchange, we also should consider the Higgs boson exchange. So we have a mixed potential that has a Coulomb term and the Yukawa term. And now you may say, well, obviously the Higgs is much heavier than the gluons, which are massive. And typically the coupling of the Higgs to these particles is smaller than the strong coupling. Sure, that's true. But what happens is actually that there is some kind of interference effect. The gluon, you may believe that the Higgs mediated potential is not long range enough, but in fact the gluon exchange already influences the wave function of the interacting particles. So how long range the Higgs exchange manifests depends on the already distorted wave function, distorted because of the gluon exchange. So there is an interference effect here that is quite important, and it's quite generic in co-annihilation scenarios. Now the co-annihilation, and so So usually, well, it can be that we have gluons and Higgs, or it can be we can have weak mediators and the Higgs. So we can go calculate the same processes, and here is an example of the result we find. Again, it's the mass difference between the dark matter and the co-annihilating particle on the vertical axis and the dark matter mass on the horizontal axis. And you can see here different cases. The dashed line is just perturbative annihilation. The dotted one is annihilation with Sommerfeld effect due to gluons. The blue one is if we include bound states due to gluons, with a gluon mediated potential only. If we include just annihilation, but also the Higgs potential, you will get the green band, and then if we include everything, we'll get the red band. And you see that the difference is quite spectacular. This calculation has been done for a coupling to the Higgs that is not small, but it is not huge either, so it is within the range of couplings that appears in the SSM. So of course, to do this correctly and or completely rather, and compare it with experimental data, we need to do this within the supersymmetric parameter space, where the coupling to the Higgs is not a free parameter; it depends on the other supersymmetric couplings. And yeah, so this is what would be needed. And in the last few minutes, let me pass on to the other effect that the Higgs can have. So what we saw to here is that the long-range effect of the Higgs as being a mediator. So what it does is it actually contributes to the Sommerfeld effect of the direct annihilation processes. It also contributes to the binding of bound states. But there is one more thing that the Higgs can do, and this is it can contribute to the formation of bound states via emission. We can have bound state formation via Higgs emission. The previous calculations I showed took into account the Higgs as a mediator, but they still considered bound state formation via gluon emission. So what about bound state formation via Higgs emission? Well, calculations have shown that the capture in the bound states by emission of a neutral scalar is actually a very suppressed process because of selection rules. This is a quadruple transition, and the highest is the moment, the multiple moment that participates in the transition, the more suppressed the process is. So bound state formation by a vector boson emission is a dipole transition, and it's significant, as we saw, by a neutral scalar emission. It's a quadruple transition, and it is not important. However, the situation is dramatically different if the emitted scalar is actually charged. And the reason for that is that the emission of a charged scalar changes the Hamiltonian between the incoming and the outgoing states. And this actually gives rise to monopole transitions. And these monopole transitions are extremely fast, even for small values of the couplings. And there is an analog of this in atomic physics. The underlying physics is quite different, but the common point is the change in the effective Hamiltonian. So the analog is that when a nucleus undergoes a better decay, what happens is that the Coulomb potential that the electrons fill changes, because now we have a different number of protons. And this change, due to the beta decay, actually precipitates extremely fast atomic transitions. So it can get the atoms ionized or excited very quickly. So again, the underlying physics is very different here, but the common thing is the change in the Hamiltonian causes very rapid transitions. The reason this is important is because the reason it is interesting here is because, there is a charged scalar in nature that we know about, and this is the Higgs doublet. So we can examine this effect within a single model first, a U1 model with a charged scalar mediator, but instead of doing that, because I don't have that much time, let me jump directly into a Higgs, into the Higgs itself. So the type of scenarios where this is relevant is scenarios where we have two multiplets coupled to the Higgs, and dark matter is eventually, after the electroweak phase transition, it is the neutral, is a linear combination of the neutral components of the two multiplets. So here we have a doublet, an sv2 doublet and a singlet. We could also have a triplet and a doublet or other combinations. So first of all, if dark matter is heavy enough, if it is heavier than 5 TeV, freeze out begins already above the electroweak phase transition, so we should consider the whole Higgs doublet, not just the Higgs boson. But even if it happens below the electroweak phase transition, there is the Goldstone boson equivalence theorem that ensures that these effects actually remain important. So here, because we have a doublet and a singlet, we have many different kinds of bound states. I don't have time to explain all the technicalities. It's quite involved, even though the model is simple. There are different kinds of bound states, and what you see in this plot here is the cross sections, thermally averaged effective cross section with respect to this time parameter, mass over temperature. The various colored lines, so the red lines is the annihilation cross-section without and with the Sommerfeld effect. The other colored lines are bound state formation cross-sections. And the major contribution here is from bound state formation via emission over Higgs doublet. And what you can see here is that these cross-sections are larger than the annihilation cross-section by orders of magnitude. Of course, you can also see that they become important at late times, because at early times, actually bound states form rapidly, but they also get ionized rapidly, so they do not deplete dark matter very effectively. This is why bound state formation becomes always important when the temperature becomes of the order or below the binding energy. And here is the result of the freeze out. We have two free parameters in this model. One is the coupling to the Higgs, so the Kalliopi coupling over here squared over 4 pi versus the dark matter mass. And the lines represent the determination of alpha versus the mass. For different cases, the red line is just annihilation with Sommerfeld effect due to the hypercharge and the sv2 gauge bosons. For the bluer line, we have included bound states also, but taking into account only the potential due to the gauge bosons and formation by a gauge boson emission. And you see it's not very important here because the multiplets we have considered are small. We have a doublet and a singlet. For higher multiplets, if we had the triplets and quintuplets, of course, it would be more important. But what makes a huge difference here is the formation of bound states by a Higgs emission. When we include this, we get this young line. And you see that actually the effect is quite dramatic. The right plot shows the effect on the dark matter density, and you see that it reaches actually 2 orders of magnitude. That's a big deal. Now, of course, you may observe that the effect appears only for large values of the coupling to the Higgs. This is not because the cross-sections are not, well, this is not because the amplitude for these processes is not large. The amplitude is very large, even for smaller values of the coupling. What happens is that there is a phase-phase separation due to the Higgs emission. But in general, if we did this calculation for higher multiplets, we would expect that the effect becomes important also for smaller couplings to the Higgs, because for higher multiplets, the gauge couplings will participate in the binding energy of the bound states, so there is more energy available to be emitted, and the phase-phase separation due to the Higgs emission is not as severe. So again, this is a rather huge effect, and this is the first study of this kind, and there are many technical issues that need to be looked at in more detail and more models to be considered, but in general, this entails a reconsideration of the Higgs portal models, which include also the neutralino score co-annihilation scenarios in the MSSM. Okay, and with this, I will just finish by saying that in general, both due to unitarity arguments and by explicit calculations, we see that in the multi-TeV regime, bound states become very important for thermal-relic dark matter, but also for scenarios beyond the thermal-relic scenario. and they have very important implications. It means that dark matter can be heavier than previously anticipated. This gives motivation for the experimental probes of dark matter, and also, of course, for building a 100-TeV collider. And yeah, I guess that's it. Thank you.
Okay, so thank you very much, Kalliopi, for this nice talk. Are there questions? So it seems everything is clear.
So I have a question. Sorry, I was in the middle of something else. Maybe I missed it. But when you were discussing the Sommerfeld enhancement, apart from the requirement of having a very light mediator with respect to the product of the coupling constant times the mass of the dark matter, I was wondering if it is also necessary to have a given type of interaction. So do all types of interactions like axial, pseudo-scalar, and so on give rise to the Sommerfeld enhancement, or is it more general?
No, the truth is that axial interactions probably give. So the important part is what potential is created by the exchange of the bosons, and axial interactions do not give rise to a Coulomb potential. They give rise to potentials that scale, that are shorter in range typically. So they scale as 1 over r cubed. Or they're spin dependent, or they're spin dependent. So in that sense, no. But on the other hand, if you have a scalar mediator with a symbol, a scalar mediator that produces a Coulomb or a Coulomb potential, it is the same for a vector. It's the same as for a vector interaction.
So I was thinking in the sense of, because the typical light mediator that one can think of is something like a Goldstone, or something like an Axion or a Mayer or something like that. So those would not lead to such long range enhancement, no?
Probably not, but one would have to look at that more detail. So,
okay.
but yeah, no, it is true that if you have pseudo-scalar couplings, then if you have a spin-dependent potential or a more short-range potential, then you will not get as strong of an effect. Which is not to say that you will not get an effect at all. Maybe there will be, but well, that will depend also on the strength of the coupling.
Okay, thank you, Kalliopi.
Thank you, Enrique. Are there more questions? Okay, so if not, thank you very much once more for this nice talk, and let's close here this seminar.
Thank you very much.